All right. Back to work. So let's review what we did in the first half. We define the running time of an algorithm. There is no running and there is no time, but this is how it's called. What is the running time of an algorithm? Here I'm looking for a word. Is a function. The running time of an algorithm is a function. Like every function, takes some input or argument and produces some output or result. What is the input or argument of this function? Fantastic. The size of the input of my algorithm. The size of the input of the algorithm. This is the argument of the function running time. What is the output? The number of times that some step of the algorithm is executed. I decide what is the size of the input, and I decide what is the operation that I do. Later on, we will play a very nice example of this. Now, when I have the running time, I consider this a big O notation to compare two running times. Let me tell you what is the idea behind the big O. You work for a company that solves the problem by running an algorithm. And your boss asks you to write an algorithm with some different characteristics. And of course, wants to know what is the running time of the new algorithm. If the new algorithm is a big O of the old algorithm, everyone is happy. Why? Because you were running your algorithm before. This one runs as well, except for that C, multiplicative constant, which typically in practical case is small. It's a small number. If it is less than 0, means that your algorithm is really good. Sorry, less than 1 means that your algorithm is really good. If the C is 2, 3, or 4, means that your algorithm is 2, 3, or 4 times slower. And then, if they really want to run it faster, say, buy a better machine. More memory, more core, faster clock, something like that. You with me? Alright, so this is a way to compare the running time of two algorithms. Running time is a very bad name, as I told you, it's a disgrace. But in practice, when you have this number, this is how long it takes to run the algorithm. So it's not that bad. So now we consider a different situation. This is the situation where your company has an algorithm that's not really good, it's too slow. And so your boss says, well, let's try another algorithm. You write the other algorithm, and it turns out that your algorithm is even worse than the one you had before. Right? If you can measure that your algorithm is worse than the one before, you don't waste time. Right? You know that it's not good enough, and you toss it, you don't have to test it, document it, try, or anything else. And so now we have this definition, big omega, that we write in this way. Instead of big O, we write omega. Omega is one letter of the Greek alphabet that sounds a little bit like the O of the Latin alphabet, which is the one that we use. And what is the condition? The condition is like before, but now the old algorithm, time a constant, is smaller than the new algorithm. So the new algorithm, the running time of the new algorithm, beside this constant, is bigger than the one you had before. Alright? If this happens, the new algorithm is a piece of junk and you can toss it away. Well, it's not a positive result, but at least you know it, right? And so the crucial part or the crucial differences are you replace this here, can you see it on the screen, with this here. Basically, you keep the relation less than or equal to, but you swap the two sides. And so, a second ago, we proved that n squared is not the big O of n. Should we try to see whether n squared is a big omega of n? So what do I want to do is to prove that n squared is big omega of n. So what is the condition here? So the condition here will be C times n, this one here. I do away with absolute values because that n, I can always take n at least 0. This has to be less than of n squared for n greater than m, and let me put here greater than or equal to 0. I have to put this one because I do away with the absolute value. So what do I have to find? I have to find the value of this C and the value of this M. All right, and what you said may be true, but here, now I would like a conclusion. Therefore, yes, for? No. No. If you take n equal 1/2, fantastic. So here, if we take n greater than 1, which means m equal to 1, what do we have here? Here I can simplify, and I have C less than or equal to n, right? And so when C is less than or equal to n, when C is equal to 1, right? And so I have that n, yes, n is less than or equal n squared for n greater than or equal to 1. And if you want to tabulate it, to see it, for 1 you have 1, 1, for 2 you have 2, 4, for 3 you have 3, 9, and so on. Yes?
Would your m not have to be equal to whatever you assign C? So if you actually assign C 5, then 5 times 1 is not less than or equal to 1 times 1?
Yes, so the idea is that that m, you try to keep it as small as possible. So now, again, if you take 1 million and 1 million, it's going to work. Yes. Also good? All right, so now finally we have the last piece of notation. The last piece of notation, which is big theta. whose complexity is g of n, where n is the size of the input. And so we say that f of n is a big theta of g of n if this happens. F of n is greater than g of n for a constant c1 and is smaller than g of n for a constant c2. So by fudging a little bit this constant, I have that f of n is bigger than g of n and smaller than g of n. At this point, we say these two algorithms behave exactly the same way. Because with a constant I make it smaller, and with another constant I make it bigger. So the difference is really a constant factor. Are you with me? And so I would guess that this is new for most people here, right? And so don't be scared. Here we have only two concepts. One is the running time. Should we say one more time what the running time is, or I'm killing you?
The number of times that a specific step has to be done.
Well, I was looking for a keyword and you didn't tell me the keyword. Function, thank you. Someone is got it. It's a function, and as for any function, we have to say what is the argument of the function and what is the result, how you get from one to the other. We make example. Here I'm giving you the concept. And so we talk about the running time, and then we talk about the big O notation, which includes big omega and big theta. And what is this big O notation? Big O of a function g of n represents the set of all the functions that grows no faster than g of n. No faster. And big omega, the one that it grows no slower than g of n. And big theta, the one that grows exactly the same. So it's interesting to know what is the complexity of some algorithms. So binary search. If you have an array and this array is sorted, and you want to see whether a certain value is there, what is the complexity? Log of n. Log of n grows very, 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 very slow. So you are incredibly happy with this algorithm. Even very large numbers, even a very large input, you can tell whether an element is in the array very, very quickly. Basically, this is how search engines work. You have billions or trillions of web pages around the web. You want to find the one where there are certain words there. It takes nothing to find, because it's this one. Linear search. You have an array, the array is not sorted, and you want to find whether an element is there. The running time is the size of the array. If you double the array, you double the time. If you multiply by 10 in the array, you multiply by 10 the time. Sorting. Sorting goes, there are different kinds of sorting. Some are good and some are not so good. The good sorting are n log n. And the one not so good are n squared. For big numbers, the difference is immense. And so these are, the efficient ones are more complicated, but they are worth doing. Then we have some algorithms which are n cubed. These algorithms are to multiply matrices. For example, if you have two matrices and you want to multiply them, the time is n cubed. Or to find the shortest path between 2 points. This is something similar. We are going to look at these algorithms. Something similar to when you do Google Maps. You're going to go from one place to another. And this is telling you how long it takes. N cube is the limit. Practical algorithms don't have a complexity bigger than n cube because it takes too much time. Matrix multiplication, people came up with very clever ways so that instead of n raised to the third power is n raised to the 2.76. And then someone was so clever that went down to 2.71. And this is going to make a very, very big difference. Algorithm to multiply large numbers, hundreds of digits. Many algorithms are n squared, like you would do it on a piece of paper. There are some algorithms that rather than n squared is 1.7 or 1.6. Again, makes a tremendous difference for large numbers. And then there are algorithms that are above n cube, and this is the twilight zone. We can't compute those things because it takes too much time. And so one is the traveling salesman. You know this problem? So the idea of the metaphor is a traveling salesman that has to visit a number of cities trying to sell his product and then comes back home. So in which order you visit the city? For example, if you are in Portland and you have to go to New York, to Washington, and Los Angeles, you can go from Portland to New York, from New York to Los Angeles, from Los Angeles to Washington, and then come back. You do 3 times coast to coast, which is very long. But you could go from Portland to New York. New York to Washington is a shorter distance. Washington to Los Angeles to New York is much shorter. So, if you have 50 cities, you are not going to solve. This is the same for politicians, right? When politicians have to go and speak in many places, depending on the order they travel, it's a much shorter trip or a much longer trip. So this is a very practical problem, and you cannot find a perfect solution. You can find approximations. And so this is why we study these things. At some point you will take 350, where you will study in detail some algorithms, and you will have to discuss what is the complexity of these algorithms. All right? Later on, we will introduce a puzzle. We will play with that and really see the running time and which operations and how you pick the size of the input for a toy problem. As far so good? Move on? All right. So now we study a couple of algorithms, and then we are going to play with them. And so the first is called the division theorem. On many books, this is called a division algorithm, which is a disgrace as well as terminology, because this is not an algorithm. This really is a theorem. It states a fact, and let's see what this fact is. You have 2 numbers. These are integers. In your mind, think about the natural number. The sign doesn't really play any role. So we have A and B, and says, look, no matter how you pick A and B cannot be 0. B is positive here. You can find 2 numbers, Q and R, that satisfy that condition. R is between 0 and B, and A is equal B times Q plus R. We will make an example. Who wants to give me 2 numbers? 27 and 4. This is my A and this is my B. All right? 4 is not a 0. It's just an observation. You are required to pick it a non-zero, right? So the theorem says, look, there exists a Q and an R such that 27 is equal Q times 4 plus R, and R is between 0 and 4. Who can tell me what Q and R are? This is a 6 and this is a 3. All right? So this theorem says, look, pick A and B as you want. B can't be 0. So pick A and B any way you want, not to 0. And you can always find the Q and R that do that. I think how to find Q and R, are you learning in grade school or in second grade? Yes?
Why can B, I think B could be negative?
Yes. Oh, to avoid that, because now you can have A and B can be both positive, both negative, one positive, one negative, so on. Some other people say, look, let's just do this for the natural number, and then the sign doesn't really play much. All right? All right, some concepts. The first one is the meaning of divide. I think this is related to what we were discussing earlier, right? It says if I have A and B integers and B is not 0, we say that B divides A if and only if there exists a Q such that A equals B times Q. We can read that one, B divides Q, or B divides A, or B is a factor of A. All right? So now that we know that concept, we can say when a number is prime, we say that P greater than 1 is prime if the divisors are 1 and P itself. And if P is 1, if P is 1, the divisor of P are still 1 and P itself, right? However, we decided that we don't call it prime. So if you have a number greater than 1, there exists a prime number that divides it. All right? Euclid was studying these things and stated some of these facts some 2,500 years ago or more. There are infinitely many primes. If you have a prime number that multiplies the product A times B, it must divide A or must divide B. If P is not a prime, this is not true. You want to make an example? Who want to make an example? Yes? So you can take P equals 6, right? A equals 2 and B equals 3. Now 6 divides 6. But 6 doesn't divide 2, nor divides 3. All right. Few more concepts. I think the people know all this. This is just a way to write it there so we can reason about this. All right. There is this fundamental theorem that says that take a number greater than 1, you can break it into primes raised to some power in only one way. And so, how do you break it? 24? 2 to the third, 3 to the 1. There is no other way to break it. So far, so good?
For the case of
23.
you want me to add
In the case of 23, you will only have a 23 raised to the 1. Because 23 is prime. Alright, the greatest common divisor. This is an interesting algorithm. This algorithm is 2,500 years old, and we are still using it, and it still works well. That's what it's supposed to do. So, what it's doing, you get the two numbers, and you find the greatest common divisor of these two numbers. They can't be more than 0. Alright? And so here there is a recursive definition. Let's read it together. If the second number is 0, the greatest common divisor is the first. The first can't be 0. If the second is not 0, what do? We do the greatest common divisor of the second mod, the first mod, and the second. So this is the reminder of dividing A by B that we saw a second ago. Should we run it on an example? So here I want to find the greatest, let me switch, the greatest common divisor of 189 and 33. All right? So 33 is not a 0. So what do? I have to find the so I write 198 is equal, 33 times some Q plus some R. Who can tell me what is this Q and this R? This is 5 and this is 24. Do you believe me? If you have a pocket calculator, you can verify. So now what do? You take this one here and this one here. So you have 33 equal 24 times, and now we have to put something here and something here. Why? Because if you look at this algorithm, it says, look, if you have A and B, B takes the place of A. And the remainder of the division, A divided by B, takes the second. And so if you look here, this is exactly what we did. Now that the numbers are a little smaller, we can do this more easily, right? So what is the divisor and what is the remainder? I'm sorry?
1 and 9.
1 and 9, thank you. You're right. All right, so because the second is not, which is this one, is not 0, what do? We bring here 24 equal 9 times plus. What is this one? 2. What is this one? 6. And so now, what do we bring there? 9 and 6. And what do we have here? 1 plus 3. And we are almost there, right? Now what do? We bring here the 6 and we bring here the 3 and we have what? 2 plus 0. And so now we have a 0, so what we conclude? 6 is the greatest common divisor. Yes, sorry. 3 is the greatest common divisor. Because 3 comes here and 0 comes here. And when the second is 0, according to the definition, when the second is 0, is the first. All right?
I'm sorry, what was the order again?
What was the?
The order that you just said. 3 was the first?
Right.
Okay.
So now, if we were to continue this one, we should we bring a 3 here and 0 here. So we have the greatest common divisor of A and 0, where A is 3, and so we are done. So there is a property that we are going to use, and is the following. If the greatest common divisor of A and B is some number C, then we can find X and Y such that this equation has a solution. So, how do we see this equation in this example that I'm doing? A was 189, the other one was 33. Yes, thank you. So there is this x plus 33, this y is equal to what? 3. This one here. Now, looking at there and solving that equation is not so easy. Many algorithms that work with this one, if you feed them 189 and 33, you get just the x and the y that solve this one. So you have there, because they are very often, they are very useful for many problems. And here you find a link to this one. Now, I don't have the network. Let me see if I can get it. Here it is. If you click here, you get this one, which is called Extend the Euclidean Algorithm, that says that you can find x and y such that ax plus by is the greatest common divisor of this one. And in some place, here it is. This is the algorithm in some pseudo language. All right. So far so good? All right. So now we are going to use some of these things for encryption. The encryption that is done in the book is definitely more interesting than this one, but it's much more complicated. So, to make your life easy, I'll do this one. This is called a Caesar code, because supposedly it was used by the Roman emperor well over 2,000 years ago. And so, what did he do? He wrote all the letters one after another of the alphabet. And then below, he wrote the letter switch to position forward. So below A you have C, below B you have the D, and so on. You see how they come about? When you run out of the letter, you get Y, you wrap around. So Y is Z plus 1 that you get A, and Z is A plus 1 that you get B. What's so good? This is not a particularly clever algorithm, but you have to put it in context. This was at the time where 99% of the population couldn't read or write. So just writing on a piece of paper probably was encryption enough. Then if you mess around a little bit later, no one would be able to read. Right? So here you have an example of that one. And I think online you find that later on a link to an algorithm that does the encryption. So how do we encrypt here? We have this function E. E takes a letter. We represent the letters with the number between 0 and 25. A stands for 0, 1 stands for B, 2 stands for C, and so on. And Z, 25 stands for that one. And what do? We multiply X, which is the input, the letter we want, by A. We add B, and then we consider the remainder of this division. This is a letter, we convert it back, yes?
So when you do the modulus, like
Yes.
you work a couple times, are you basically imagining there's like a parenthesis around?
Yes. Good point, I'm a little bit sloppy. When we work in Z26, everything is more than 26. So now, when you encrypt, you have to choose A and B such that E is a bijection. Why? Because otherwise you have two letters. When you encrypt, they go to the same. When you have to decrypt, which do you keep? The first or the second? Sometimes it will be one, sometimes it will be the other. So this has to be a bijection. Yes? Alright, so we have to understand when this is a bijection. To play with this one, let's do the following. Let's get a spreadsheet. Office Calc. So let me put here 0. Here I put the one above plus 1. Perfect. So here I compute this one. I compute this one times, let's say 3, plus 4, and I do everything in mod 10. Instead of 26, I make a smaller example, which is a little bit easier to understand. All right. So, can you see this well? This would be the encryption of the digits rather than the letter. 0 is encrypted to 4, 1 to 7, and so on. And you see how these look scrambled? Can you see any order in this one? Not really, right? And so now we want to know when this is a bijection. So here I use, if you look at the formula here, sorry, small, what I do, I pick this one, multiply by 3 and add 4. Let's try to do the opposite. Let's try to multiply by 4 and add 3. Ha! Is no longer a bijection. You see that is no longer a bijection? Why is no longer a bijection? Right, the 2 and 7 are mapped to 1. Right? And also, so it's not injective. Also, no one goes to 4. So it's not bijective. And of course, because they have the same 10 elements here and 10 elements there, If it is not injective, it's not bijective, and the other way around, obviously, right? So here, when I do this transformation, I want to know what do I have to pick for A and B so that this is a bijection. And I have a theorem that says it. The theorem says, look, suppose that I go from the natural mod n, when n in the example I did was 10, for the letter is 26, or whatever you want, and I do ax plus b mod n, so this is bijective if the greatest common divisor of a and n is 1. Alright? So this explains why in the small example I did before, the first one was a bijection, the second was not. N is 10. In the first example that I did, A was 3. What is the greatest common divisor of 3 and 10? 1. But when I pick 4, what is the greatest common divisor of 4 and 10? 2. It's not 1, it's not a bijection. Alright? So do you think that this is a good encryption? It's a terrible one. Why is a terrible one? Who can tell me a good explanation why is a terrible one? Yes?
Because it's easy to solve.
Right. Why is it easy to solve? Very good.
Computers are pretty fast. You could do it with a
Well,
If you have, you don't have to do it by just you have A, B, C, D, O, Z, and I want to show
well, of course there has to be an index. Yes?
There's no variation once you figure out how, if you can solve a small set, then you can
So, but if you have to break this brute force, try all possible cases. How many possible cases there are? At most there are 26 for A and 26 for B, right? Actually less because they have to be, the greatest common divisor has to be 1. So what is 26 times 26? A few hundred? And a computer takes a millisecond to see all of them and see whether there are words you can read or not. Right? How would you make it stronger?
make it a clear number.
Right, instead of considering one letter, where the cases are 1 to 25, try to consider 2 letters, right? So, how many are the cases now? 25 squared. So, you have to work a little bit harder. What if you consider 4 letters? What if you consider a block where you have 1,000 letters? Now, we run in the millions or the billions. And so, in principle, this could be better, right? Alright, so now we know how to encrypt. This has to be a bijection, because otherwise we cannot decrypt. To be a bijection, we need that A and N are co-prime. The greatest common divisor is 1. So how do we decrypt? So given the F that we use to encrypt, the decryption D is of the same form, is the Kx plus C mod N. And how do I find this K and this C? Well, AK plus NN has to be equal 1 for some K and N. M I toss it because I don't care. But K is the one that I plug here. And how do I find C? C is the one that when I encrypt, I get 0. So, let's pick the example that we had before. All right, so let me write the one that I had before. Mod 3 times this one plus 4 mod 10. So this was the good one. So now this is the encryption. Now I wanted the decryption. So for the decryption I have to do what? For the decryption, I have to solve this AK plus NM equal 1. What is A? 10. What is, sorry, A was 3. What is this one? N was 10. Who can find the K and the M? All right, he says -3 and 1. Very good. So, because we compute in mod 10, what is this -3? We find it in this way. We have 0, 1, 2, 3 until 9. Here we have 9, 8, 7. I'm wrapping around, right? So this is -1, -2, -3. Very good. So let's try this one here now. So this one will be mod, yes, mod this number times 7 plus which element goes to 0? These two, right? 2 mod 10 da-da. What do I have? Here with this function I encrypt. Now with this other function, if I take this one decrypts, this is the composition, and the composition is the identity. So all the things that we learn fit there perfect. Alright? So, let's look at, oh, sorry, I'm past my time, right? I was going until 1:30. Tell me, if I get carried away, this is more interesting than other things. So say, hey, wake up, the time is over. Sorry to keep you.